Hi there. We are done chapter 5 and we are heading into chapter 6. So chapter 6 will be our fourth chapter. Chapters 5 and 6 are the two calculations-based chapters. Some people find them to be the most challenging. Some people find them to be quite gentle, depending on how comfortable you are with your calculator. And with some basic algebra, which is what we've been doing. We've been rearranging equations, we've been substituting into equations, and we've been solving for quantities. How many molecules, how many moles, how many grams. Now, as we move into chapter 6 here, chapter 6 is going to be using all the things that we learned in chapter 5. So if you struggled through chapter 5, you're going to find yourself having to go back and maybe revisit some of the things that you struggled with in chapter 5. But I'm going to start into chapter 6 here. Now, before I go any further, I just want to quickly pull up the textbook, if it doesn't disappear on me here. So the textbook for chapter 6, oops. The textbook for chapter 6 starts off, oh, come on. With a concept called stoichiometry. So stoichiometry is what we're going to be doing for all of chapter 6. Stoichiometry, I'm going to expand this here, I can't make it stay expanded. It says it's the study of quantitative relationships between the quantities of reactants and the quantities of products that are formed. It is the tool that answers the questions that we see in the figure and countless others related to reactions. Now, I just want to move down to the pause and check questions here. Right? Now, if I look at the people in the figure, in figure 1 there are 3 lab technicians. Remember, a technician's a person who's been to college for probably 2 years and is now working somewhere. So the first one is a pharmaceutical lab technician, and it says she's trying to synthesize an experimental drug. How much reactant do I need in order to make 1 gram of the drug that I'm making? Okay, so there's a question. How much of the reactant do I need if I want to make 1 gram of drug? Okay, number 2 here at the bottom is an analytical chemist. An analytical technician says, I'm using a chemical reaction to test for the presence of a drug. If 0.456 grams of a certain reactant was consumed, how much drug was present? Right, so we can, again, use quantities to predict how much drug is present. The first one asked, how much reactant do I need? This one's now saying, how much product am I going to make? And then the third person over here is an engineering technician. Again, may have gone to Mohawk College or Niagara College or Fanshawe or George Brown. It says, I'm helping to perfect a process to make the drug on an industrial scale. If I have 10 tons, over 10,000 kilograms of one reactant, how much of the other reactants do I need to use if to have the minimum amount of waste? Remember, in a chemical reaction, the balanced equation tells us how much of each reactant we need to make a certain amount of product. So if I come down to the pause and check questions here, the 3 questions are, why is it important to know the amounts of reactants and products in a chemical reaction? If you look at the example that they give there in question 2, it says 2 potassium atoms react with a Br2 molecule, bromine, to make 2 potassium bromide molecules. Okay, so that's what the reaction is. Now, the goal here is always typically to make something, right? That's what chemists typically do, right? We're chemical reactions are happening and reactants are turning into products. Now, that being the case, if the goal here is to make a product to sell, right, which is what business is about, it's about making new pharmaceuticals, making new food substances, making new industrial chemicals. If I know how much I need to sell, then I need to know how much of the reactants I need to make it. Now, if I look at the reaction here, it says 2 potassiums react with a Br2, and each of those Ks will take one of the 2 Brs to make a KBr. If I had a third K in there, we did this in chapter 5, if I put an extra potassium in there, at the end of the reaction, 2 of the potassiums will have reacted with the Br2 to make 2 KBRs, and the extra potassium will be left over. In other words, it was wasted. We put it in there and we never used it. Right? It was still sitting there at the end. And sometimes it's hard to get back once it's mixed with the KBr. So I'd rather have the right amounts of K and Br2 to make the right amount of product. If I only put 1 K atom in there with a Br2, then I may not get any product at all, because that K will take one of the BRs, but that leaves a BR left over. And remember, BR doesn't exist on the planet. It's one of those 7 elements that's diatomic. It will only be Br2. So question 3 there below that says, what is stoichiometry? Remember, we just said stoichiometry is looking at the quantities of reactants that are required and the quantities of product that will be made in a chemical reaction. Okay, so that's really the basis of all of chapter 6, right? Everything we're going to do in the next, I'd say, week and a half to 2 weeks. It's a pretty big chapter, and I'm just going to encourage you to keep thinking about the calculations that you did on the chapter 5 test. Now, as we move into topic 6.2 here, it talks about using, using balanced chemical equations, right? So it's all about making sure that when I have a balanced chemical equation, I know how much reactant I need and I know how much product I'm going to get. And if there's multiple reactants and or multiple products, I know that I'll end up with the right amount of everything involved. So further on here, they're going to look at a chemical reaction that occurs between carbon tetrahydride here, CH4, and 2 oxygen molecules, creating a carbon dioxide gas molecule and 2 gas water molecules. Okay, remember, 1 plus 2 makes 1 plus 2, right? So that's my balanced equation. And that's ultimately going to tell me how much of each I need. Now, that's telling me that 1 molecule of carbon tetrahydride plus 2 molecules of O2 make 1 molecule of CO2 and 2 molecules of water. Or, as we learned in our last chapter, that's telling us that 1 mole of CH4 plus 2 moles of O2 make 1 mole of CO2 and 2 moles of H2O. And we've got our equation going back to our last chapter that says if I know little n, if I know the number of moles, then I can calculate I can calculate little m, the mass in grams. Okay, so that's where we're going with this in chapter 6. It's trying to understand, come on, Notability. Trying to understand how the moles fit into our chemical equation, and then ultimately how we can use our concepts of balanced equations and moles to fulfill the law of conservation of mass. Right? The idea that in any chemical reaction, the total mass of reactants will always be equal to the mass of products. If I put more reactant in than I need, then it won't get used. So when I'm saying the mass of reactants here, is the mass of reactants that gets used up or consumed will be equal to the mass of products that's being formed. And the reason why that law works is because I know that all of the atoms that were present at the beginning are still present there at the end. And because it's the atoms that have mass, then the atoms that are still present will basically contain the same amount of mass. And the reason why the atoms that were there at the beginning are still there at the end is because we cannot create or destroy atoms in a chemical reaction. So if they were there at the beginning, they have to be there at the end. So when I look at this reaction here, and it says N2 plus 3 H2s make 2 NH3s, it's balanced because I have 2 nitrogens on this side and 2 nitrogens over here, and 6 hydrogens here and 6 hydrogens there, and it's balanced. Now, that being the case, that's again telling me about what's going to happen in my test tube. right? Ultimately, I know that 1 molecule of N2 will react with 3 molecules of H2 to make 2 molecules. And if I double the reaction, if I put in 2 molecules of N2, I will need 6 molecules of H2, and I will make 4 molecules of NH3. I doubled the reaction, or times 10. 10 plus 30 makes 20. Instead of 1 plus 3 makes 2, 10 plus 30 makes 20. And then because molecules and atoms are so small, in Chapter 5 we said we can't really talk about molecules and atoms. We need to talk about moles of things. So my reaction that I had at the top here that says N2 plus 3 H2s makes 2 ammonias is telling me that down here 1 mole of nitrogen plus 3 moles of hydrogen makes 2 moles of NH3. And what I know is if I know the number of moles here, mass is equal to the number of moles times the molar mass. The mass is equal to the number of moles times the molar mass. Okay, this was all over the Chapter 5 test, right? And this is what we do in chemistry. So the molar mass for N2 is 28.02 grams per mole. And I have 1 mole here. So I'm going to have 1 times 28, which gives me 28 grams of nitrogen gas. I have 3 moles of hydrogen. So I know that I have N is 3, little n is 3 moles. The periodic table tells me the molar mass for hydrogen, which is 2.02 grams per mole. So if I take my 3 moles times 2.02 grams per mole, I will get 6.06 grams. Okay, just like 1 mole times 28.02 gave me 28.02 grams. And over here, NH3 has a molar mass of 17.04. So if I take my 17.04 times the 2 moles that I'm seeing here, I will get 34.08 grams. Now, that's telling me specifically, as the chemist, how many grams of everything am I going to be working with. 28 grams of this product plus of reactant plus 6 grams of this reactant will make 34.08 grams of NH3. And if I actually look at the chemical reaction, okay, the chemical reaction tells me that if I have 28.02 plus 6.06, which is 34.08 grams of reactants, I will make 34.08 grams of product. So, in our textbook, there's one question, so I'm going to finish with that today. That's the end of my note. I want you to do question 7 on page 212. So let me go back to the textbook here for a minute. So here's page 212 here. 212 is the one that says a CH4 reacts with 2 oxygens to make a CO2 and 2 waters. Okay, so I'm going to take that reaction and I'm going to go down here and I'm going to look at this chart, this table 6.3 here, table 6.1 here. And it tells me the same reaction is in the green box at the top there. CH4, which is called methane, reacts with 2 oxygens to make 1 carbon dioxide and 2 water vapors. They've drawn them all here as colored atoms, as balls that represent the atoms, and to show that the carbon was on the left side over here in methane, and it's still over there in the carbon dioxide. And that the 4 O's that were here in the oxygens are now 2 of them connected to carbon and 2 of them in the middle of H2O's. And the 4 hydrogens that were present over here in the methane, 2 of them connected to oxygen to make water, and the other 2 connected to the other oxygen to make water. Right, so the reaction there tells me that 1 molecule of CH4 reacts with 2 molecules of oxygen to make 1 plus 2. The same thing about moles. 1 mole of methane gas reacts with 2 moles of oxygen to make 1 mole of CO2 and 2 moles of water. Oh, but I know what a mole is. For methane gas, mass equals number of moles times molar mass. Number of moles is 1, molar mass is 16.05, so I end up with 16 grams of methane being required. I can figure out how many grams of oxygen are required because I need 2 moles, which is little n. Can't write on the screen here, I'm sorry. It's little n. And with that little n, I multiply it times the molar mass because mass equals number of moles times over and over and over. Right? That is a chemist's life. Mass equals number of moles times molar mass. Exciting, eh? Should be. So, and then I'm going to get 1 mole of carbon dioxide and 2 moles of water. And again, multiplying the number of moles times the molar mass will give me the number of grams of each. And I can see from this, like I had before, that if I add up the number of grams of reactants on the left side and the reactant side, I get 80.05 grams. And if I add up the number of products, grams of products that are produced, I end up with 80.05 grams. Now, question 4 down there says, what are the 2 meanings of the coefficients in balanced chemical equations? Right, 2 meanings of the coefficients. The coefficients are the large numbers out front, and it tells me how many molecules are needed to react and or are being produced. It also tells me how many moles are needed to react and how many moles of product are being produced. Number 5 says when 1 mole of methane reacts with 2 moles of oxygen, how many moles of carbon dioxide are made? We know that 1 mole of carbon dioxide is made. And it says the term 2 O2s, it tells you that 64 grams of oxygen is consumed when 1 mole of methane goes. Use a calculation to describe why that's so. Again, mass equals number of moles times molar mass. Little n times big M. So the question I'm asking you to do for homework, right, just to get into chapter 6 here, is to make a table similar to table 6.1 there, but instead of using CH4 plus 2 O2s, we're going to use the equation that's given at the bottom. 2 H2s plus an O2 make 2 H2Os. Right? And basically produce that same chart for yourself so we can, again, just keep using mass equals number of moles times molar mass. Right? And recognizing that the numbers that are in our balanced chemical equation, the coefficients that are out front, are telling me how many moles I need for a reaction to happen. Okay, so I'm going to stop there for today, and I will come back to 6.3 tomorrow. Okay, take care. Have a good night.